Okay, so this is my senior project. It is the work that I've done with Dr. Curtis Credo in the MacLeod Institute of Simulation Sciences, which is a laboratory here at Chico State University. It is funded by Office of Naval Research, Science and Technology, and the project that I've been developing is called STAR, which is an abbreviation for System of Transparent Application Refactoring. And this is my poster, and this is a tool that I've built for Dr. Curtis Credo using C++ and LLVM Clang compiler APIs, and also Git. Although I think everyone uses Git, but I just put it here so I can have symmetry inside of this box here. Okay, so I will explain you what my project entails. So reading at abstract box, it says that high-level synthesis is the process of converting a model of a circuit system created in a GUI program such as Simulink into a hardware description language file for the purpose of verifying that circuit through simulation in FPGAs. What it basically says is that the area that Dr. Curtis Credo is working on, high-level synthesis, is a process of taking a GUI diagram, a diagram or a model of a circuit system created in a software called Simulink. If you're familiar with Logisim, it's the closest analogy that I can think of. And we want to execute that circuit inside of FPGA. We do that by generating a hardware description language file, for example, Verilog. So by automating this process, a door into FPGA-based development is open for users lacking sufficient expertise in model digital design techniques. So if one can simply create a drag and drop a certain circuit in Simulink, and then having the option to export it into a Verilog file, they can do the digital logic simulation without actually knowing digital design techniques. And my tool is specifically for automating this process. It is a tool that is used for automating the process of high-level synthesis. So Simulink does not support generating hardware description language files by default, and its generated C code has numerous incompatibilities with existing high-level synthesis tools that take C code and they generate Verilog code out. So Simulink takes the GUI model that is created by the user in its interface, and it generates a C source code representation of that. But not all code constructs generated by Simulink can be implemented in the FPGA's hardware, necessitating an automated refactoring, which is where my tool comes in. So my software is designed to handle all such possible code constructs that might be generated by Simulink and refactor them with compatibility, with priorities being compatibility with the high-level systems tools and efficiency. So if there is a chance to optimize it, then we want to do that as well. So this is the process. On the top, we have a Simulink model. That's what the user creates in their Simulink GUI program. So the bluish boxes represent actual data, and the boxes on the left side with the arrows represent the programs that modify that data. So Simulink IDE has a package built in called SimLencoder, which takes the GUI model and it outputs a CPU targeted C++ source code, which is a representation of that circuit system. So it's basically a software which outputs you computer generated source code, and then we have another tool called Vivado HLS, which takes in FPGA targeted C++ program, and it generates the FPGA hardware description language code. It generates a FPGA hardware description language code, but the problem is that the FPGA has a relatively different memory model than a CPU. So not all C and C++ CPU targeted C and C++ programs work on FPGAs. So what my star tool in the middle is doing is it transparently refactors the CPU targeted C++ program into an FPGA targeted version as input into Vivado HLS, which uses it to generate the hardware description language file. So my star tool, as you see in the middle, it uses Clang LLVM compilers API to parse the code. Then it uses custom heuristics to find those incompatible code constructs and perform in-place file replacements. So in order to be able to read the CPU targeted C source code and translate it into FPGA targeted source code, you need to use a compiler API such as LLVM right here.
Can you scroll your cursor over? We
easily.
Can't see that square.
Clang LLVM has its own API which facilitates easily reading source files into memory in a program and generating an abstract syntax tree without the need for specifying an explicit parser and lexer as you would do that with Flex and Bison. So it's a more modern compiler toolchain as opposed to Flex and Bison. So these are the completed program transformations that the star tool now does. So it removes some functions unsupported by the FPGA logic blocks. So it replaces Mem Copy and Mem Set with a for loop that copy elements in an array into elements into another array, and it replaces hypot function with a manual computation that does the hypotenuse calculation. Now, the reason why these functions are unsupported by the FPGA is that hardware description language files, for those of you who don't know, are actually not implemented as software but as hardware. Whereas a CPU targeted C++ program is loaded into the random access memory of the CPU, an FPGA targeted C++ program is ultimately transformed into actual logic gates, actual hardware. So there is no operating system, and the C standard library functions, they do system calls. They rely on the operating system to do some operations for them. And since FPGAs do not have an operating system, we cannot use those functions. If those functions are included in the source code, they need to be refactored and replaced with something performing, having the same implementation. So Another refactoring was replacement of all dynamic memory allocations with static memory, because FPGAs do not have a heap. They cannot use dynamic memory. They can only use static memory, because static memory gets transformed into logic gates of an actual circuit inside the FPGA. So we cannot do dynamic memory allocation because we cannot change allocations of logic gates during the runtime. We can only change it during the synthesis, but so we cannot have a self-modifying circuit. So that refactoring was completed by Dr. Curtis Credo, and then he assigned me to integrate his backend logic into the overall star tool that I'm creating. And then another refactoring was the removal of redundant assignments and unused variables that just take up space in the code, and space is an extremely important consideration. A code space is an extremely important consideration in FPGA design. Those are actually utilizing the static analysis based refactorings, which we will see later. Then another quite basic refactoring was replacement of indirect pointer-based memory accesses with direct ones. So instead of having a pointer to an object, you just use that object instead. This is because FPGAs have they don't have pointers. Pointers are not supported. They have like a flat memory addressing scheme, and you can only access local addresses. You can't jump to arbitrary locations in the memory. And then the last major refactoring was removal of indirect recursion by breaking the function called dependency chains, because recursion is not supported in FPGA. So if there is recursion, we have to break it by identifying the function called dependency chains and breaking them. So moving on to the fifth box.
Wait, before you move on, I have a question.
Yeah.
Is there a runtime stack?
You can think of it as such, but actually in the FPGA targeted C/C++ program, when it's taken in as input by the Vivado HLS, it generates Verilog code, a hardware description language code, which gets translated into logical circuits that are actual hardware devices. So instead of programming the software, you're actually programming the hardware of the computer. So we can have an abstraction of a runtime stack, but that's not how it's implemented internally.
Okay, go on.
So box number 5 basically displays me that the abstract syntax tree based refactorings that I implemented and what those are. So Clang LLVM you basically give it a C++ input source code, and it takes that source code, parses it, lexes it, and it gives you an in-memory data structure, which is the abstract syntax tree of the input source code. So for those of you who haven't taken compilers, an abstract syntax tree is a tree like data structure which represents the source code. It's basically like HTML, the JavaScript DOM tree. If you know, JavaScript code represents your HTML web page as a tree that you can traverse to insert various elements and remove various elements into the tree. So this is a similar concept, except that instead of HTML code, we're having C++ code, and the abstract syntax tree is a representation of that. So I can have my program manipulate that abstract syntax tree representation to perform replacements. So it only does structural analysis of the abstract syntax tree or the structure of the source code to perform refactorings, and I'm using custom heuristics, which are basically traversing the tree in various ways to identify those problematic code constructs, and then equivalent in functionality replacement code constructs are created that are compatible with Vivado HLS, as we see on top.
And so you basically modify that tree?
Not directly. So as far as I know, Clang's the EST, the tree generated by Clang compiler, is read-only. So I cannot directly modify it. I cannot directly export it back into the source file. I actually look for. I use it to find those problematic code constructs, but I generate text replacements into the source file.
Okay.
Yeah, and these abstract syntax tree based refactorings are designed for modularity. So in the actual C++ source code, that in the actual C++ code of the star application, I've designed them so that each AST-based refactorings is its own module, so that they fit together like that, and different refactorings can be enabled or disabled independently. So for example, if you want to enable or disable various refactorings or optimizations, you just pass it certain command line flags, and based on the flags that you pass in, you have the option of enabling certain refactorings to be performed and disable other refactorings. So moving on to the 6th box, this describes the static analysis based refactorings, which I think were the hardest part of this project. Basically, for those of you who aren't familiar with static analysis, in contrast to the tree-based refactorings, which only look at the structure of the source code, the static analysis-based refactorings look at the behavior of the source code under certain conditions. Tree-based refactorings can't tell you anything about the behavior of the program. They just tell you about the structure. But if you want to debug your program and automatically find issues and fix them that might occur under certain runtime, under certain runtimes. So Clang compiler has its own static analyzer, and I found a way to invoke it programmatically from C++. So it calls the static analyzer, it calls the compiler to perform behavioral analysis on the input code and find bugs that could occur under certain execution paths. So on the right side, we have a control flow graph. So for example, you go down, you execute a statement, you go down, then you go back up, maybe that's a loop, then there's a branching condition, maybe that's an if statement, the if branch is on the left and the else branch is on the right. So the static analyzer basically constructs a control flow graph like that, and then it walks around along the different branches in that graph. It walks along the different possible execution paths to identify bugs and problems. So that is done internally by the static analyzer. So that's not something that I had to implement. However, it's this feature of walking along the control flow graph is something that's internal to the compiler. It's not accessible to the outside world, to application developers that want to use it as an API. So it's not a publicly available API of the compiler. Yeah, so because using the static analyzer in your own C++ source code isn't natively supported by Clang LLVM API, so I created my own API by extending existing classes that are provided by the Clang compiler and by reading the source code of the compiler itself. So because LLVM Clang compiler is an open source project, you can see the source code and read it, and I found the actual place in the source code in the compiler where it invokes the static analyzer, and based on that, I kind of reverse engineered that, and I created my own API to allow me to call the static analyzer directly from my C++ program and then get the results of that analysis and use that to perform refactoring, to perform source code replacements, eliminating those bugs that could occur under certain execution paths. So I've created the API for that, but I've only used that so far for elimination of dead code. And dead code just means redundant assignments and unused variables. For example, if you declare a variable and then you assign to it and you never use that anywhere else in your program, well, that variable is taking up space in your program. And if on the right-hand side of the assignment, you're doing some computation and returning the result, then it's also eating up your time complexity as well. And you're never using that result anywhere. So because going back to box 3, because Simulink is a dumb application, the source code that it generates frequently includes the dead code, a bunch of dead code that is removed. It is removed by the start application, by my tool, because we don't want dead code. So now I will perform a live demo of my application. So this is just the project. So as you see, it includes a whole bunch of different modules, such as remove Mem Copy module and remove hypotenuse module. So I've already built it. It's already made. And in order to run the refactorings, on the Simulink generated source code, I type run make a refactor. And when I do that, you see a whole bunch of text, a wall of text. What it's actually doing is you're seeing my C++ code, the start application code, in doing the analysis in real time. And for each problematic code construct, it shows that on the screen. It finds the problematic source code in the actual input source code. Then it highlights, it actually copies and pastes the actual string from the source code onto the terminal. Then it pastes the file name and the line number, which are the long lines of text that you see running around. The reason why they're long is just it pastes the absolute path in. So it displays what was the problematic source code construct, then it displays the complete absolute path to that source code file and the line number in that source code file where that problematic code construct is, and then it displays the replacement, so what it was replaced with. So right now it's running the refactoring on all the source code files, on all the input source code files that are generated by Symlink. So there are 4 of them currently, and Dr. Cortescudo is working on creating more. But here we see that it performed 3,168 total refactorings. It gives you some analysis. It performed 8 mem copy replacements, 4 mem set replacements, and it basically replaced 43 pointer with arrays and so on and so forth. I won't bore you with the details. Instead, I'll show you how it what was the result of doing the replacement. So here I am using a tool called Meld, which it's able to compare to different source directories. I'm comparing the refactored version of the code with the unrefactored version of the code. So on the left is the refactored version of the code, and on the right is the original version of the code. So I'm going to take a look into one of the files in the project, the .h file. So on the right you see the original version, and on the left you see the refactored version. So on the right you see that there were several void pointers. Those are actually pointers that will be attached to the dynamically allocated memory. So you would do a malloc call and return the pointer and save it into that void pointer. So instead of that, it actually statically allocates them. So it gets the data type and the size of the array from the actual malloc call that is associated with every single one of these pointers, and it edits the declarations of those pointers to be declarations of the static memory arrays. So moving on down, this is another one of those replacing the pointers with the arrays that they will be allocated. So all of this code was untouched. If I go all the way down, you can see that it added a new function. It added a new function declaration, and we'll see that shortly. So if I go to the .c file, this thing is basically it removed that variable from the right side to the left side. It deleted that variable because it was no longer needed. Then if I go all the way back down, it renamed some of those functions, those function calls. Then here we get to the more interesting stuff here. So if you see this if statement, it was deemed unnecessary by the program. So it's an if statement that does nothing. So here it is being removed. And finally we get to the mem copy. So mem copy here is just used to copy elements from one array into another. So because mem copy is unsupported by Vivado HLS, my code takes that and it refactors it into a loop. It just copies elements from the source array to destination array by the number of elements, and all of that information is gotten from the original mem copy call. here's another one of them. And this is where I take the hypotenuse call and I replace it with this big old long expression which computes the length of hypotenuse manually based on the length of the legs. Yeah, so this is another Mem Copy refactoring, more of those Mem Copy refactorings. And then there are certain of these replacing the arrow operator with the dot operator. That's replacing, instead of having a pointer, instead of having indirect accesses, you now use dot accesses. Because pointers are unsupported by FPGAs, you would actually need to access the memory loop. You would need to get the object that pointer points to, and then use that object instead of the pointer. So you would have a direct memory access instead of an indirect memory access.
All right, you're getting close to running out of time, so you need to wrap it up.
Okay, so here, one last refactoring I want to demonstrate is that here you see it actually created a whole new function. It created another function here, which is the void complete system IO step minor void. So it created that function in order to break up the indirect recursion. Part of the solution involves creating a new function and using that and calling that function instead of calling the original function that breaks up your indirect recursion. So those are the changes that I had made. And if I go back to the terminal, I can type in make verify to run. So make verify basically takes the refactored source code and it runs it under different conditions, under different parameters, to test whether or not the behavior of the refactored version of the code is the same as the original unrefactored version of the code. And it displays results match reference values if the behavior of the refactored version of the code during the runtime matches exactly the behavior of the unrefactored version of the code, and it does that by checking for the outputs that the program produces. So as we see here, all the results match the reference values, which means that the Star application refactoring tool performed successfully. So that's basically it. That's all I have. That is the end of my demo.
Did you, when you refactor, do you do it all in one pass, or do you refactor one component, generate C++, new C++ code, and then parse that C++ code again and do the path over and over?
Yeah, so the replacements are performed in place, and there everything is modular. For example, this macro right here defines a list of individual modules.
What I'm asking is, how many passes do you make?
Okay, so it does one pass, 2, 3,
okay,
4, and 5, and 6 passes. It does 6 passes in total And there are some refactorings that are combined in a single pass. It combines some of the refactorings. If they can be run in parallel, then they are put as part of the same pass. But having multiple passes, that's just for having refactorings that build on top of each other.
Yes.
And the only reason why I have multiple passes is because some of the refactorings have direct dependencies on previous refactorings, but the ones that don't have direct dependencies on the refactorings, they are run within the same pass in parallel. And that's and the parallelization is automatically done by the Clang compiler API.
All right, any other questions? Let's clap. You're allowed to unmute your microphone when you clap, but.
Thank you.
All righty. There we go. Curtis even joined us for the clapping part. All right.